Chapter 7 is actually broken up in only 2 sections, and what I'm going to do is I'm going to break up section 2 into 2 sections in itself. First part of section 2 that we're going to be looking at today is using, section 2 is labeled as using the law of universal gravitation. Now what we're going to be looking at today with this video is, the orbit and how fast and how long it'll take things to orbit around a certain heavenly body, okay? So if we look at planets and satellites, how do they orbit? Well, if we're looking at something that is orbiting the Earth, the object, they fall towards the heavenly body, so in this case Earth, at the same rate that Earth's surface curves away. So what that means is they're going as fast as they are dropping, and that causes them to be in an orbit with Earth. So if we kind of Alright, so here is Earth. I know, it's a lovely picture. And if we had a cannon and we shot it, if it's powerful enough and low enough, it would kind of go a little bit and curve. Now if we had that cannon a little bit higher and a little bit faster, the round would go a little bit further, and then if it was really high, it'd be able to escape the gravity in orbit around the Earth. And what we can do is, the way that we can calculate out what is the speed of a satellite orbiting Earth, or honestly any heavenly body, if we know what that mass of the heavenly body is, we can use this formula. So, I don't know why I put nu, but velocity, v, is equal to the square root of our gravitational constant times the mass of Earth over the radius. Now, if we want to figure out how long it takes for an object to orbit, if we're looking at Earth, once again, since we got a lot of satellites around here, time period is equal to 2 pi times the square root of r cubed, so the radius cubed, over our gravitation constant times the mass of Earth. And what we can do is, yes, we can put in other planets and everything if, like I said, if we know what the mass is and all that. So, let me get a calculator real quickly. So let's kind of look at an example. And we're going to kind of run through this and see how this works out. It says, all right, assuming that a satellite orbits Earth 225 kilometers above its surface, given that the mass of Earth is 5.97 times 10 to the 24th kilograms, the radius of Earth is 6.38 times 10 to the 6 meters. What are the orbital speed, and period? Okay, so the first thing is we need to figure out what is the full radius that this satellite has, because it is 225 kilometers above the surface. Now the radius of Earth is 6.38 times 10 to the 6 meters. So what we're going to have to do is take 6.38 times 10 to the 6 meters. And we're going to add on to that 225 kilometers. Now, this is in meters, 225 is in kilometers, so we need to convert that over. So 225 times 1,000. .25 times 10 to the 5th meters. So we're going to add those two numbers together, and that will give us our full radius of what, from the center of the Earth, where is the satellite at, distance-wise. 6.38 times 10 to the 6 plus 2.25 times 10 to the 5th. And I'm coming up with, so let's kind of put that in scientific notation. Let's say 6.61 times 10 to the 6 meters. Okay, so finding its orbital speed or its velocity. Alright, so it's g, that's our gravitational constant, 6.67 times 10 to the negative 11 newtons times meter squared per kilogram squared times the mass of Earth. Well, the mass of Earth is given to us as 5.97 times 10 to the 24th kilograms. If you hear other noises, that's just my daughter. Now, over R. Well, our R is 6.61 times 10 to the 6 meters. So, let's see what we come up with. So, square root of 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th divided by 6.61 times 10 to the 6. And I am coming up with 7,762 meters per second for an answer. Now, looking at the period, t, all right, so 2 pi square root, now our r, same thing, 6.61 times 10 to the 6 meters, and that would be cubed all over 6.67 times 10 to the negative 11th newtons times meter squared per kilogram squared times our mass, 5.97 times 10 to the 24th kilograms. Alright, here's our setup. If I can get a hold of paper, there's our setup, so let's run through that. So 2 times 3.14 times square root of 6.61 times 10 to the 6 and that is going to be cubed, divide by 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th. I'm coming up with a period of 5,348 seconds. Okay, now, how am I getting that from all the information that we have in there? Well, if you kind of remember, Newton is 1 kilogram times meter per second squared. Okay, so when we take everything through with newtons and everything, we're going to be, and we square root it, we come up with seconds. So 5,348 seconds. Well, let's kind of put that into a little bit more substantial unit that we can possibly use. One of the things that we can possibly do is, well, let's take it to minutes. Alright, so 1 minute over 60 seconds. So 5,348 divided by 60. We're at 89 minutes. Okay, so about an hour and a half is the time period for this satellite to orbit around the Earth. And as I said, I mean, we don't always have to stay with Earth. We can go with any kind of planet that we can possibly want to if we know the radius and the mass. Okay, so hopefully this helps you. If you have any questions, let me know, and I will talk to you later. Thanks for watching.